Thank you very much, Rob, for this very nice talk. If you have any question, please raise your hand in the chat. In the meantime, I want to say I find it amazing that you build yourself like such an experiment. It's very nice. Also, probably floated because like this trapdoor, like it has some gravity, so like it's shaken, as you were saying, in a different way that it would be like if it was thermal fluctuations, of course. But I found it very nice, and indeed, like the way you explain it at the end, like the reason why like this is, I mean, not violating anything, and how it can go as much in one direction than in the other. I find it so very. I will keep this image in mind.
Yeah. So for me, I've found the Smoluchowski argument that the trapdoor will be in thermal motion. I think I heard it in a course on thermodynamics when I was a student, and I've seen it in various textbooks. But I've never seen this argument about drawing a time reverse path to make it really rigorously prove, let's say, at a hand-waving level, that you can't violate the second law. I'm sure someone must have thought of it, so I'd be very happy to have a reference. I don't believe it can be original, so I'd be happy if someone has a reference for it. Then I can add it to my talk next time I give it.
Okay, so thank you very much. And if anyone has a reference of this kind, please put it in the chat. I think we will have to move on to the next talk. I mean, I apologize, we accumulated a lot of delay already. So, so please welcome Liliana Arrachea, who's a full professor at the National Atomic Energy Commission in Argentina. So it is my pleasure to introduce you. And she's going to speak about heat to motion conversion from quantum active matter. So please, Liliana, you can start. Thank you very much.
Thank you very much, Leah, for the introduction. So let me, So thank you again, and thank you to the organizers for coordinating such an interesting and diverse program.
I'm sorry to cut you.
Can you hear me?
Yes, but we don't see your screen. So far, we see the screen of Rob, at least I do.
You don't see the screen?
I see the screen of
just a while. Sorry. Now?
Okay, yes, perfect.
Yeah, okay. So let's start again. Yeah, so I was saying that I'm connecting from the very south of the world, from Bariloche in Patagonia. I recently moved from Buenos Aires to Bariloche. Let me fix something. Can you see the pointer? No.
Can you move the pointer?
You don't see any pointer?
No.
So there is something weird. Now?
Yes, we can see.
No, but no, it's in the wrong mode. I think, well, you don't see the pointer. Okay, I try with my pointer. Otherwise, I have to connect from another computer. Sorry. Something.
Otherwise, you can go back to the previous mode of it should be fine also.
Sorry. No, there's something weird. I'm not allowed to.
But maybe we can try without the pointer for now.
I connect from another computer. Let's see.
Hello.
Yes, we can hear you.
Okay, sorry for the problem.
No, don't worry.
Yeah. Yes. Now you see the pointer.
Can you move it? I don't
Yeah.
see it. No, I don't see it.
Oh my God.
Maybe we can try without it, and if...
Yes,
Ah, yes, we can see actually. I just saw something.
you started seeing that.
I think if you click, we can see like a red dot.
Okay. So let's move on. Sorry. So I was telling you that I'd like to tell you about a recent work done in collaboration. Now it doesn't work. Yeah. In collaboration with Alex Jorger Penner he's finishing the PhD in FU Berlin. Ludmila Biotti, who is a postdoc at ICTP Trieste, and two senior collaborators, Rosario Fazio from ICTP and Felix von Oppen from FU Berlin. So I'll start saying a few words about the concepts of active particles and active matters. I think this subject will be covered more seriously later this week. So what is an active particle? An active particle is a small machine, is a particle that is able to convert energy that is taken from the environment and to process the energy that is taken as a fuel and convert this energy into motion. This is an active particle, and there are very beautiful examples in nature, in biological systems. All of them are described with the classical thermodynamics. And the most, the nicest one is this example in this movie, which is a cartoon for a kinesin, but there are many other examples, and prominent ones are these micro swimmers. A collection of these active particles can self-organize in the presence of noise without any leader, and generate this kind of collective movements, which prominent examples are these birds. This picture is taken in Rome, but there is a process that is observed also in nature, in many species, also in penguins and in many others. And the question is if it is possible to implement this kind of mechanisms in the quantum realm. And indeed, there are already a few proposals that appeared quite recently. I'm going to very briefly review them. The first one, I think that you don't see so I'm basically presenting without a pointer, sorry. For some reason, yeah. But anyway, let me continue. One of the first recent works that appeared in this subject focused on the collective behavior of active matter in a quantum system. The quantum system is described in terms of this Lindbladian dynamics. These are several particles that are obeying some hopping processes in a lattice, in addition to some some correlations induced that tend to align the spin. So these particles contain spin, and these hopping processes are correlated in the sense that they tend to favor the alignment with the same magnetization of the neighboring spins. This is, for example, taken into account in this P operator below. A very similar idea was formulated and published more recently. This is in the Lindbladian dynamics is substituted in this example by a non-Hermitian hopping processes, but the ingredients are very similar. There is also some ferromagnetic interactions, some flipping processes, and the hopping of particles with spin. This work focuses on the possibility of generating correlated motion in the sense of the active matter I mentioned before. This is a more complex example where there are two kinds of subsystems named A and B. Also, each of these subsystems contains a collection of spins of two-level systems, qubits, which due to the interaction with some environment experience some non-reciprocal interaction, effective non-reciprocal interaction, and the result is a collective effect, which is in this case related to the synchronization of these spins. About quantum particles with the focus of single particles that behave as an active particle. There are, I can mention mainly two recent works. One is this one. The idea here is to mimic in a quantum example, the self-propelled classical particle. Here, a driven particle is considered in contact with some environment, and the focus is on analyzing, also describing in terms of Lindbladian dynamics, the motion and the net motion of this particle in this context. More perhaps complicated example is this proposal in the quantum walk. Here, there is also a combination of non-Hermitian hopping and non-Hermitian transitions in a particle containing 4 internal degrees of freedom. Now, I'm going to comment on our work. So our work was recently posted to the archives. And this is a proposal for a quantum particle. Not the focus here is not on the collective effect, but on the how to get some particle that is able to convert, in this case, a heat taken from the environment into a net motion. So this is the model for the particle. The particle is very simple. It contains it's a two-level system under the action of, so it can be regarded as a spin system under the action of a magnetic field generating a Zeeman interaction. And the particle can move in in a lattice, in a one-dimensional lattice, in our example, with the following structure. It can it can jump to neighboring sites in the lattice, but these jumps can also come along with some spin flip processes in the form which these are expressed in the terms of some spin orbit coupling that is represented by this vector G that couples with the spin degrees of freedom. So it can simply jump without changing the spin, but it can also jump changing the spin. So the two ingredients are the particle jumping in the presence of a magnetic field that acts on the spin, and in the presence under the effect of some spin orbit coupling. So the internal degrees of freedom of the particle are connected with two reservoirs at different temperatures. So the two reservoirs are modeled by simply bosonic excitations, and it is important that the connection takes place asymmetrically. This means that the intensity, so the amplitude of the connection, in this case indicated by this square root of gamma, as well as the operator, the spin operator entering the interaction may be, and it's important that they may be different. So as we have a translational degree invariance in this problem, we can transform this Hamiltonian to the momentum space. And this is the result for the Hamiltonian of the particle after we transform to the momentum space. So we have here a momentum indicated by this ket K. The Hamiltonian is diagonal in K, and it represents a particle in the presence of a K-dependent magnetic field, which is represented by this lambda here. So lambda is a vector that is a result of the magnetic field epsilon and the spin orbit coupling, which has some K dependence. So as the particle moves in K space or populates with some probability the different K space, the spin orientation changes according to this effective magnetic field lambda. So delta, not lambda. So this is the velocity for the particle. We can calculate now the velocity of the particle by tracing with the density operator, the velocity operator, which is defined here. It contains some trivial part, which is this epsilon k. This epsilon k is simply a cosine-like dispersion relation in this lattice, but it also depends on the combined effect of the magnetic field and the spin orbit coupling, this delta K. In equilibrium, this mean value of the velocity is, of course, expected to be 0, but as the internal degrees of freedom of the particle are contacted to non-equilibrium environments, because the two baths have different temperatures, this velocity may have a finite value, and this is what I would like to convince you about. So we solved the problem by this Limbladian solution. We find the rho k, the reduced density matrix for every k, by solving this Limblad equation, and given this result, we assume at this point for the translational degrees of freedom to be a simple thermal distribution. And from this, we can compute the mean value of the velocity. And this is the result we show in this plot downwards. In the left corner of the screen, the result of the mean velocity as a function of the difference of temperature, and also in the as a function of the mean temperature of the two reservoirs. If we perform a linear expansion in delta T over T of the solution, we get this expression where, of course, we see that the mean value of this velocity depends on the difference of temperature. So if the two reservoirs are in equilibrium, we don't have any mean value of the velocity. It is equal to 0. While we can identify in this structure a sort of Onsager coefficient in some linear response picture, a linear response description of this problem, and the delta T over T square can be identified as an affinity. So this is the solution, and we see from this solution, even at the level of linear response, which are the ingredients that we need in order to get a non-zero value of the velocity. Of course, we need this delta T different from 0, but we also need different couplings, asymmetric couplings to the reservoirs. These are here represented by different values of these parameters xi, to the hot and the cold reservoir, and also some structure and particular orientations of the spin orbit and the effective magnetic field. So here they are summarized. We need, in order to get a non-zero mean value, we need different couplings, non-vanishing, hopping, spin orbit coupling, and Zeeman splitting. And this is the behavior that we can analytically obtain for the different temperature regimes. So for the very low temperature, we find that this velocity vanishes exponentially. For high temperatures, it vanishes as a power law, and there is some optimal temperature in between. Now the question is, what happens so far? I considered the coupling of the particle to the reservoirs only at the level of the internal degrees of freedom. And this is actually which enables the particle to get the fuel from the environment. The question is, what happens if we also include some momentum relaxation, so some coupling to some additional bath of the translational degrees of freedom. So the question is, should we still get this quantum active motion, or it will be completely washed out? And for this reason, we examined the problem under the contact of the translational degrees of freedom with some external phononic-like environment. This is represented by this Hamiltonian. So we have now some Lindblad equation, which contains the coupling to the internal degrees of freedom. This is contained in this ds. It is the same as the one I previously considered, but we also include this contact to the phononic bath. So now the solution can be factorized in the way it is written below, where the R refers to the bold R refers to the internal degrees of freedom, while the R0 in front of the equation of rho contains the effect, describes the effect to the coupling of the translational degrees of freedom. Within this situation, we can, for this, and also for this particular model, I forgot to mention that we consider different type of baths, of phononic baths. These are modeled by this new, which where they can have different powers p in the spectral density of states. Okay, so for small k in this particular model, we can write some effective, so perform some small q expansion and write some effective drift diffusion equation that can be at least formally solved. In particular, we can find this closed solution for the power p of the phononic bath, but it anyway can be solved numerically. So before showing you the results for the numerical solutions, it is important now to have in mind that we are going to face a situation where we have two different time scales. So there is a short time scale which is related to the spin relaxation time. This takes into account the connection of the internal degrees of freedom with the out of equilibrium reservoirs, and there is a long time scale which is related to the relaxation time due to the coupling to the phonons. So the previous results, where I didn't take into account the momentum relaxation time, are still valid within the time scale between this TS, the short relaxation time, and the momentum relaxation time. And these are the results. So here is the result of the solution, and the numerical solution of these equations. So this is the mean value of the velocity as a function of time. We can see that we start from a thermal situation where we have a zero velocity. The system evolves due to the coupling to the out of equilibrium reservoirs at the typical time scale TS, gets some finite value of the velocity. But then at the later times, Tm, the coupling to the phononic path plays some role, and the value of the velocity may change. The way it changes is really very difficult to predict, and it depends a lot on the parameters. In particular, in this example I'm showing you, it depends a lot on the density of states of the phonon bath. For instance, in some cases, the velocity when the phononic bath plays a role vanishes again, but in some other cases, it changes a sign, and the value, the mean value, is even larger than without the phononic, the effect of the phononic bath. So this is something interesting, but the combined effects of the two baths is really difficult to predict. In any case, what I would like to stress at this point is that the phononic bath doesn't wash out the effect of getting a finite value of the velocity. We still have a finite value of the velocity in spite of getting the coupling of the translational degrees of freedom to some extra bath. So the last point is about the possibility of identifying in this velocity quantum features. For this reason, we calculated this velocity correlation function. So this is the definition. It can be calculated by recourse to the so-called quantum regression theorem, basically given the Liouvillean, the velocity can be calculated as indicated in this equation. And what is interesting here is that in this explicit solution, we can identify some oscillations. So the oscillations in time depend on the delta. I recall you that this delta was the effective field experienced of the particle, as which is a combined effect of the external field and the spin orbit field. And I show you the results, which are much visible. We can here identify these oscillations, which have all the features of Rabi oscillations within the short time scale. So in the long time scale, when the phononic bath plays an important role, these Rabi oscillations are disappear, but within the short time scale, they are there and they reflect precisely the is a quantum effect which reflects the oscillations of the spin in the presence of an effective magnetic field. Of course, these oscillations, this zoom shows the behavior for different temperatures. As the temperature goes lower, the oscillations became more important. So this is, with this I finish. This is a summary. The ingredients we identify in order to get some active particle in the quantum realm is the combination of the spin-orbit coupling with the magnetic field. This effectively breaks time reversal symmetry. We also need asymmetric coupling of the internal degrees of freedom to non-equilibrium reservoirs. This is the fuel. And we have verified that the effect of getting some finite velocity of the particle